high-rate Wi-Fi broadcasting in quad scenario via lightweight coordination of multiple access points. This work has been done with my co-advisor Konstantinos Poussonis, Professor Giuseppe Kerr, and Professor Keith Chug, and Kaidong Wang. So Wi-Fi has been around our life everywhere. Does it work? Well, it's supposed to be working, right? Everybody use Wi-Fi. But let me give you two examples that Wi-Fi is not working. Specifically, Wi-Fi doesn't work in large scale. So this year's International CES draws thousands of people's attention to show the cool stuff from the industry. Whenever there is such a crowded scenario, Wi-Fi becomes a problem. Actually, in fact, the presenter of each company has urged their audience to turn off Wi-Fi device so that they can conduct their presentation successfully. Another example is from Super Bowl. Every year, American football event has drawn over hundreds of thousands of people to the stadium. Here's some statistics. Last year, the Wi-Fi supporter actually deploys over 900 Wi-Fi access points to support over 30,000 users. However, the Wi-Fi performance is notoriously bad, and the supporter has been working hard for years to solve the problem. And rumors goes that this year they will go even higher, like 1,300 Wi-Fi access points. But the crucial problem here is that the densification of Wi-Fi access points doesn't solve the problem. It incurs intercell interference that negates most of the gains. So in fact, NFL has forbidden any individual live video service, streaming service to your phone through Wi-Fi. And it's been hard to upload and share your videos to Facebook by just using your phone in the stadium. So can we fix this spectrum crunch? Well, theoretically, there is a good solution, multi-user MIMO. There's been tons of research on multi-user MIMO that's discussing how to reuse the bandwidth. A couple of system work includes AirSync, MIMO, OpenRF. So MU-MIMO provide concurrent transmissions for multi-users, multiple data streams, but it requires heavy coding, like space-time block codes, automatic codes, and also it requires heavy coordination between all the access points. All the access points should have tight clock synchronization, and they have to monitor the channel state between each transmission pair constantly. So these issues make it not scalable. The best Wi-Fi chipsets that I know of has only 4x4 multi-user MIMO, which means it can support 4 users simultaneously. So let's take a step back and see what we really need here. For a stadium, for a live video broadcast, we need a concurrent transmission for a single broadcast channel. We don't want any heavy coordination. We want it to be light. We don't want any clock synchronization, so we can be cost efficient. And we don't want any stream level coding, so it's practical. It can process in real time. Well, one solution is coordinated transmission. What I mean by that is to transmit the same data packets from multiple transmitters simultaneously, so that the receiver doesn't recognize data interference, but as a constructive combination of the signals. Coordinated transmission is not a new idea. We have coordinated multiple point protocol for LTE, and we always learn the barrage relay network in our wireless network courses. In fact, some company like Trellisware has been building real stuff with a barrage relay network, but they have to rely on special hardware, and it's not Wi-Fi commercially available. So in this work, we propose CobiCast. It is a lightweight Wi-Fi compatible coordinated transmission solution. It addresses several Wi-Fi specific PHY challenges, and it designs a MAC protocol that is Wi-Fi compatible for the coordination. In the paper, we also demonstrate that CobiCast achieves more than 10-fold gain in Wi-Fi broadcast rates. So in the following of the talk, I will give you some introduction about basic challenges of Wi-Fi coordinated transmission, and some 5-layer techniques that we use to address those challenges through our experiments. Then we move our experiments to real-time Wi-Fi scenario. We design a MIC protocol to coordinate multiple transmissions. Lastly, we evaluate the gains of our scheme through a large-scale simulation to see actually how much gain we can get through copycast. We built our testbed using warp boards, software-defined radio. The transmitters are controlled by a central server. The server transmitted the same Wi-Fi packets through a switch to all the transmitters, and the transmitter will transmit the same signal together to the receiver, which will be then uploaded to the central server for further analysis. So in the paper, we discovered some challenges for doing so. First of all is the block boundary detection. The first packet we send using our testbed is actually not detected by the receiver because it has a wrong block boundary detection. We'll discuss that later. The second one, the biggest challenge, is the cooperative time offset. We use the word cooperative to define the time offset and both time offset and carrier frequency offset between the transmitters, to differentiate that between the traditional time offset defined between transmitter and receiver. And also, the most challenging scenario is that when both the CTO and the CCFO exist. Okay, the first challenge. So the Wi-Fi packet is recognized by its preamble. The standard says the Wi-Fi preamble consists of 10 repetition of short training sequence, 2.5 repetition of long training sequence. Each LTS consists of 64 samples. So in the traditional unicast case, the LTS is specifically designed for producing only one autocorrelation peak for each training sequence. So whenever the Wi-Fi packet comes, the receiver, by doing autocorrelation, will see two correlation peaks so that it knows which sample corresponding to which sequence, and then it knows after 32 samples, the block boundary starts. However, in our case, assume we have two transmitters. Suddenly we have 4 correlation peaks. If we just by counting naively the number of peaks, we will miss the correct boundary by 64 samples away. So we fix this by choosing the first pair of peaks that are 64 samples away from each other, and use that as the block boundary detection. Okay, here comes the main challenge, the CTO and the CCFO. So for the CTO, again, in the 2 transmitter case, I give you an example of CTO equals to 200 nanoseconds. We can see the channel response on the lower side of the figure. Traditionally, if there is a unicast channel where there is a stable, no much changing, then the channel should be flat. But in this case, the channel is wiggling due to destructive combination of 2 waveforms. And specifically, these 2 fading dips of subcarriers will cause sporadic erroneous constellation, as you can see on the right-hand side. And that's the problem CTO. What's the problem CCFO? Let's first take a look at traditional CFO case, where there's a CFO between transmitter and receiver. Well, there are standard ways to solve that. In fact, Wi-Fi packets consist 64 subcarriers, among which four of them are known pilots, so that the receiver can compare the received pilots to the known sequence and see how the phase will drift over time. You can see on the lower side of this picture, it averages over the 4 subcarriers to calculate the average drift, and then use that average drift to compensate for other data subcarriers. So that way you can see we can still get a clean constellation. However, in our case, where there is a CCFO between 2 transmitters, although the receiver can still track the phase correctly, but in Wi-Fi standards, there's no way to track the magnitude of each subcarrier. You can see that the magnitude of the subcarrier will fade over time because the rotation of the relative phase of 2 transmitters will change over time. So the constellation also proves that although you can estimate the phase correctly, the magnitude will phase into the origin, towards the origin. And what makes it worse is that the CTO and CCFO combination scenario, where you will just see a full of mass constellation. Fortunately, it's just a constellation. We can apply coding on top of it to solve that. In fact, Wi-Fi standards already have forward error correction codes. In most commercially available Wi-Fi devices, such as our phones, we can see half-rate convolutional codes implemented. It is also implemented in our software-defined radio. However, it's not strong enough. It has only about like 7 sample block length. We replaced that with LDPC code, low-density parity check codes. In Wi-Fi standards, it has almost up to 2,000 sample block length. And it is also part of the 802.11 NNAC standard. But however, it does not often see in our phones and commercially available datasets, chipsets, sorry. And the second technique we apply here is the constellation demapping. So the traditional way is hard decision demapper. What it does is that it applies a grade on the constellation. And to see each red point is the transmitted, is the received points of an OFDM sample. Whichever block it falls into, it will just apply 4-digit bits on that. It is hard decision because it's not reasonable, right? Because it loads information of how much drift does the point have from the transmission point. Instead, we use a soft constellation demapper, which describes the error as a drift like this, and decode over the drift instead of the 0 and 1 bits. So you can see intuitively this makes much more sense because it has all the information of how much drift does the point have compared to the transmission point. So the literature has shown that soft decoding has 2.5 to 4 dB gains in receiver sensitivity. What it means is that it can tolerate channels that is 2.5 dB worse in SIMR. Okay, so with those two techniques, we evaluate our PHY-layer, copycast PHY layer. Here I give you one example of our evaluation. We evaluate a 16 QAM modulation coordinated transmission with LDPC code and different CTU and CCFO scenario. The y-axis shows the average bit error rate. The x-axis shows the different CTO. We vary from 0 to 600 nanoseconds. And different lines shows different CCFO scenario. So you can see that 16 QAM case, we can tolerate up to 400 nanoseconds CTO and up to 1,000 hertz CCFO. In the paper, we have the full evaluation of different scenarios like QPSK, 16 QAM, 64 QAM, with different combination of CTO and CCFO. So to give you some context of the numbers, a 40 megahertz commercially available oscillator, which has a 10 parts per million inaccuracy, would yield 400 hertz frequency offset. So that makes 1,000 hertz requirement quite loose. Actually, it's just using oscillator we can achieve that. However, the CTO requirement is a bit hard. In fact, even the OFDM cyclic prefix lasts for 800 nanoseconds. So 400 nanoseconds is quite critical. So time to make it real. We designed a MAC protocol to achieve those requirements, so to synchronize the transmitters within 400 nanoseconds. So we replaced the laptop with another access point. We call this primary access point, PAP, which can then coordinate all the SAP, secondary access points, for the coordinated transmission. So we also remove the synchronization cable so that each AP is running on their own frequency, free-running oscillator. And our design is totally Wi-Fi compatible. So the idea is to first let PAP contain the channel following CSMA protocol. And then once you have it, it will send a over-the-air trigger to all the SAPs. We call this a send now message. Upon receiving that trigger, all the SAPs will send the data packet together. we use an acknowledgement autoresponder to send that packet. The acknowledgement following the standard should be sent in 16 microseconds, which is the SIFS. So this way we have two benefits doing that. The first one is that the two boards are supposed to be sending the packets in 16 microseconds, so they can be as simultaneous as possible. The second benefit is that within SIFS, nobody else can grab the channel. The channel is preserved by PEP contention, and so the SEP can use it freely. However, there's a drawback in this approach. 16 microseconds is quite a short time, so that we don't have time to find the correct packet through upper back layer. We have to preload the packet into file layer, so upon receiving the trigger, it will fire immediately. So we have designed a ping-pong buffer-like mechanism. Details can be referred to the paper. So next, we evaluate our design in real time. To see what PEP and SEP is actually transmitting, we put a power splitter in between the transmitter antenna and the board. So through an oscilloscope, we can see the PEP actually first transmit a signal message, and the two SEPs will transmit the data packets together. Here, we snoop the MAC destination address as the PEP address, so that the PEP will know this packet is towards me, is directed to me. Then following the standards, the PEP should then send an acknowledgement. So this acknowledgement proves that our coordinate transmission actually works. It is correctly received and acted. Next, we will evaluate how tight can we synchronize the two SAPs. We measure the time between the two transmission of the SAPs. Here's the CTF of CTO. We have conducted over 14,000 count of the transmissions, and we get a mean average of 93 nanoseconds. And over 95% of the packets has lower than 300 nanoseconds CTO. So lastly, we evaluate our scheme in this large-scale simulation to see how much gain we can actually get. Traditionally, if we broadcast directly, we have considered a cluster of 4 access points here with only 3 available channels. So there would be interstitial interference in the blue 2 APs. We call this scheme vcast scheme. A way to solve that is to shut down the other 3 APs and increase the power of the PEP to cover the whole area. We call this scheme a PEP only. But this is not practical in real-time scenario because you have to reassociate the users from those 3 APs to the PEP, which is time-consuming and not practical. To get the best possible theoretical value, we relocate the PEP to the center of the range. Again, this is not possible because relocation in real time is not possible. So lastly, our copycast scheme actually coordinate 4 access points to use the same channel to transmit the same packets. We call this copycast. Okay, so we then model a conference hall internet square and compare the 4 schemes together. We put the users and the APs uniformly distributed in the square. And here shows the Shannon rates and quantized rates of the performance. From the figure, the axis shows the number of APs. We densify the number of APs deployment. On the y-axis, you can see the broadcast data rates. So the figure shows that copycast actually has 6x gains in the bcast mode. And for the non-practical scenario, it has almost twice the performance as well. How does it perform in even larger scale? We then model a large Colosseum into a circle and put users and APs uniformly distributed. And the rates here, we show that copycast can gain even more in large scale. Here we have an AP cluster of 36, and we actually achieved over 120 megabps in the broadcast rates. It is 15 times bcast rates and even 8 times, 6 times in the non-practical scenario. So here draws the conclusion. In this paper, we designed and implemented Copycast, a coordinated high-rate Wi-Fi broadcasting system. We explore and address several challenges in Wi-Fi specific PHY scenario. And we have designed a Wi-Fi compatible MAC protocol for the coordination. The simulation demonstrated an order of magnitude higher improvement in broadcast rate and achieves over 100 Mbps broadcast rate, which can support at least 10 high-definition live video streaming channels. So in the future, we would like to replace the receiver with real mobile devices and test our gains with a real video streaming application. If that works well, we will try to prototype and deploy in the real stadium. Okay, thanks for your attention.